very briefly remind what I was telling you about last lecture overboard, while putting some material here, and then I'll switch back to presentation. Basically, what so maybe even before that. So there is this site, and I forgot to put here. Well, it's my main site, but then there is courses, and I already put notes. So, and today lecture, 2 lectures are there already. Well, and actually some extra material. There are also, so I put this presentation, but there are also notes, and notes are basically not completed. It's probably a lot of errors. It's what we are planning to put with my course of Volodya Cherniak as a review. But in any case, you can maybe some you can try and see if you can see. Okay, so now what did we do? I introduced graphical model. Let me put it on this side so you would remember, because we'll continue with graphical model. So I actually mentioned I introduced one, but then I used another format, and there are multiple formats. There are certainly more than, I don't know, 5. And practically, well, in many cases, transformation from one to another is rather straightforward. So it's just a matter of notations. Yeah, so in one, my basic notation, basic case, I was discussing probability of state sigma, and I was writing it in a factorized way. So it's a factorization means that it's a product of functions, and then my functions work on vertices of a graph. Let's say this is the graph, and A in this case runs 1, 2, 3, 4, and then sigma A residing. Well, it's a vector which I associated with if A is 1 with this vertex 1, and well, 1 contains, well, it's a vector of length 6, 1, 2, 1, 1, 3, 1, 4. So my original variables, therefore, sigma A, B, my base case was binary alphabet, and well, sometimes I was using plus minus 1, sometimes I was using 0, 1, but in other cases I actually didn't specify what is alphabet. So alphabet maybe longer, and actually maybe even continuous. So that's again, my variables are on edges and factors are on vertices. Let me maybe write another model, which I kind of mentioned but didn't emphasize, and we'll be using it today. Mainly this one, but also another one, and another model is built on a bipartite graph. It's actually called factor graph model. So, in particular, error correction code and decoding of error correction code, and many other models can be, well, are normally used in this format or traditionally used in this format. So then variables were associated with one side of this bipartite graph, so, well, circles. And in this case, well, not to confuse myself, first of all, and now you, I usually use index I in this case for circles, and for squares index alpha, so Latin and Greek. And variables are over here. Well, I was also alternating between sigma and x. Let me use x here, so it's xi in this case. And index alpha was associated with factors. Well, with bipartite graph, for example, like that. And then probability of a state x will be product of over alpha, and here functions will be associated with alpha. Well, will be indexed by alpha, and in this case, x alpha is a vector which I construct according to this graph, well, depending on degree of this node. So this factor have 3 variables entering this factor, so it will be 1, 2, 3, respectively in this case it will be x1, x2, x3, just for example. Okay? So that's variables on vertices, and factors are also on vertices, but on the other side of the bipartite graph. Well, I also was mentioning Ising model. An Ising model is a model when, well, it's yet another model, yet another representation. Maybe let me put it here. And representation was like that. So it's graph again. Variables, graph now not necessarily bipartite, whatever graph. So variables are on vertices. And let me 1, 2, 3, 4. So let's say x1, etc. Those are my original variables, very much like in this case. Probability of a state in this case is a product of edges. So factors are associated with edges, and well, let me write it in this format: ij, and one particularly useful form which normally used in physics, so we put particular these factors in a particular format. Exponent of minus what we call energy. Okay, so I'm already aligned. I just wanted to be on the board when I put it down. Let me maybe, okay, energy, and energy will depend in this case of xi, xj. Let me index it like that. Okay, so it's well, physicists and other experts usually call it Ising model, but well, there are other names in this case. I'll be using Ising model. And what I was telling you about yesterday, the day before, right? So I was posing in all those cases, mainly in these, but of course questions extend to all those 3 cases. Question of maximum likelihood, right? So computing marginal probabilities and computing partition function, and that's what I'm discussing. So it's always finite graph. What we discuss this story of dynamic programming, which is exact on the tree. We reinterpret it as a graph local equations, and those equations we call belief propagation equations. I emphasize that those equations have a universal form, and that motivated people to apply it to loopy graphs as heuristics. And then I reformulated those equations as coming from a exact variational principle, but with a substitution, with an approximation, and this variation principle applies to what I call beliefs, and beliefs are probability distributions which approximate or attempt to get as close as possible to peak. So this original comparison was Kubla-Clark comparison. Mean field, right? So that was first variational principle, first attempt. It gave low bound on partition function, but I emphasize that even though it's one-sided, it's kind of loose. And belief propagation can, well, that's another side. Of course, belief propagation was correcting mean field, but even though this correction empirically is pretty good, it can be on either side, right? So it may be above or below actual partition function. But in any case, this function which we got after this belief propagation substitution, and probably I'll write it down, I'll put, so that will be open. So I'll write it to this model. So this belief of a state sigma. Oh yeah, and sigma is of course a full vector for all components of my variables. In this case, associated with edges. In the case of belief propagation substitution, so let me put it this way: belief BP. It was in this format. So this ansatz that we had. So that's if you would use one of possible mean fields, but then it was a correction, kind of unusual one, this product of terms downstairs in a denominator, product over edges, and here I had beliefs associated with edges. Right? So when I substituted this form, well, and of course, let me drop this BP, so still will be BP. When I substituted it in an exact Kublai ladder functional, I got what we call beta free energy functional, right? And then I was emphasizing that, so this was this beta free energy functional. So I want to minimize this functional over all possible beliefs, and beliefs which are consistent, and consistency is well, basically a relation between beliefs associated with vertices and beliefs associated with edges. Yeah, let me actually may write it down because it may be useful. So if I take one particular edge, and if I'll marginalize, if I'll now try to relate it to belief associated with vertex by doing marginalization with respect to all components of sigma A but sigma AB. Well, I already got a question from Alek about this notation, so let me maybe restate it again. What this notation means, so it's set minus, sigma A, set minus sigma B. It means that I fix, so this is a bigger vector, and this one is a component of this vector. So I fixed one component, particular component associated with AB, and sum over all possible values, or values of all other components of sigma A. And therefore, what I have on the left depends only on sigma AB. So this is consistency, and of course I need to write it for all edges and actually for all vectors. So I can write it from both sides, from the side of A and from the side of B. So that was a consistency which I also assume when I do the substitution. So beta free energy was derived, and then beta free energy at a minimum, if I want to minimize over all my B's, I'm getting this belief propagation solution for beliefs for probabilities. And I was also telling you, so that was, well, it leads to estimation approximation for partition function, because at the minimum beta free energy is a log of partition function, so approximation for log of partition function. But I also was stressing that in this beta free energy, there are two types of terms, right? So what I call self-energy and then entropy. So entropic terms is like B. And if I drop entropic terms, I'm more or less getting approximation for maximum likelihood. I'm sorry, for maximum likelihood. And that was a story of linear programming. So let me maybe now put I don't see it, but that's okay. Yeah, so let me now jump to this part of the first lecture. Yeah, so that was here, and briefly repeat it because there are a few things which I really wanted to emphasize, and I don't think I managed to do it last time. and I in fact modify a little bit notations to make it cleaner. So, right, so I'm still working in this format, but now I basically prefer, because I want to discuss maximum likelihood, this optimization problem. Instead of maximizing f, I can also express f as exponent minus e, and again, physicists call it energy. So maximization, maximum likelihood, most probable state corresponds to minimization of energy. And that's exact. And now let me remind you, walk you rather fast to this linear programming formulation in this format, because I wanted to emphasize one thing which will be useful in basically the next lecture, the material of next lecture. So from here, which is my original optimization, stated in terms of x, right? So it's basically, you can think it as of general purpose optimization, and here I don't even specify alphabet, so any alphabet. Well, this sigma capital basically stands for alphabet. And I even don't assume that different variables are from the same alphabet, maybe different. Right, so now there is this trick which allows me to reduce my general purpose, basically, optimization problem to, well, linear programming over those beliefs. And again, linear programming is a minimization, well, minimization, in this case, minimization of a linear expression with respect to variables for which you'll be optimizing under a set of linear constraints. So this is my objective, and it's linear in dx. So I put this integral over dx, assuming that x may be alphabet, may be continuous, but think of it as just a sum. But in any case, this objective is linear in b, and constraints are also linear in b. So that's exact transformation, right? It's actually useful to know that in principle, any optimization can be stated as linear programming. Of course, in principle, it's a very big vector, right? So because x, I should introduce those b's for all possible values of x. And if it is continuous alphabet, infinitely many. But in any case, it's linear programming, it's exact polytope, and then I can actually interpret my belief propagation in the following way. I first modify my exact polytope in this form, so I extend the space from state space, which is already large, b of x. I introduce these beliefs associated with vertices and yeah, right. Actually, let me backtrack. So here I'm discussing it in this format, in the format which I put on the left. So bipartite graph. So my variables are so it's a factor graph model. So my variables are on the right, my factors are on the left, right? Just a little bit more convenient to do it in this way. So I introduce beliefs associated with vertices. Variables. I introduce beliefs associated with factors, and then I basically define those bi and b alpha, and that's what I wrote in here. Bi is what? First b alpha. I basically sum or integrate over all variables but x alpha. Right? Integrate my original b of x. Just definition. The same about bi, and but bi I prefer to express very much like I wrote in here in terms of b alpha expected b alpha. And yeah, let's use some normalization. So far it's definition of b alpha and bi. I just extend my polytope, right? So it's kind of innocent. But then I'm doing a relaxation. What does it mean, relaxation? Relaxation means that I get rid of some constraints. When I'm removing constraint, well, it's called cutting plane, right, in the optimization literature. When I'm removing constraint, and I'm doing minimization, I possibly not getting to optimal, but I certainly getting low bound. And that's why I'm showing it in here. And okay, so what do I remove? I remove everything related to bx. Whenever bx enters, like here, I just got rid of it. So a lot of constraints threw it away. I also threw away definitions of b alpha because it depends on bx. What is left in here is only b alpha and bi, right? And okay, and end result is that I'm getting this LPBP, and it's the relaxation of exact. And so I have again linear programming, which is much smaller. So it's why linear programming? Because it's still linear functional and I have linear constraints, right? And this formulation is exactly equivalent to this beta free energy formulation if I threw away this B log B terms, this entropy. So I didn't emphasize it last time, but wanted, even though it was, well, I had it on the slide, but now I wanted to emphasize it. Okay, so that's right. That's what we had well already discussed, and there is also kind of important thing which you can do with optimization. You can go to dual, right? Well, I guess majority of you know what it means, right? Well, those of you who don't, so basically, well, kind of a bit naively, forget about inequalities for a second and think about equalities. So all those equalities, well, description of this constraint, description of this polytope, they should be considered as constraints. And what we do, we introduce Lagrangian multipliers, right? So like for this one, we introduce respective Lagrangian multipliers. And then we maximize over those, what does it mean introduce Lagrangian multiplier? You literally, well, take it b minus whatever is on the left, put it on the right. And then bi xi minus this integral, you multiply by respective, I don't know, lambda, whatever your notation will be for Lagrangian multiplier. And you add it to objective, you form Lagrangian. And then this problem becomes equivalent to, instead of mean, you're getting max mean, right? And you maximize the respect of Lagrangian multipliers. But then, what you can also do after this step, you can do minimization over your original beliefs explicitly, and you arrive at this dual formulation. Right, and all those psi's, here the phi, the respective Lagrangian multipliers, and well, actually, you can get rid some of them. In fact, you'll end up only this phi, and it gets this interesting format. So it's optimization problem, and of course, because it's linear programming, duality theorem tells me that when I do dual of my linear programming, I'm still getting exactly the same result, right? It's a convex optimization, in particular, because it's linear programming, so duality doesn't change the value. So if I'll be evaluating this, well, if I'll solve this problem, answer will be equal to what I have in my original linear programming. And this form is, well, just look at, compare it with exact optimal expression which I started from. I actually have almost the same form, and I can modify a little bit my original optimization. Well, what did I do? In original optimization, I have minimum over x, right? So those are my original variables. So I have minimum over x, and now I introduce a fictitious variable, phi, And you can check that because of this constraint, I just added, well, constraint tells me that this sum is equal to 0, and I just added 0, right? So I didn't do much. But compare those two formulations. So here, they basically almost looks very much the same, on the exception of the fact that there is mean and there is sum, right? And here there is mean and there is sum, but they're in a different orders. And that's basically another way to see how, well, right, and another way to understand this belief propagation, and well, rather useful. So those variables which basically, well, this phi, this Lagrangian multipliers, you can think of them, well, especially when I was modifying my exact optimization, you can think of them as a so-called reparameterizations or gauges. And the reason I emphasize them here, introduce them here is because they will be main players in today's lecture. Okay, so let me now, right, and by the way, this type of formulation and this transformation to duality is, well, I basically borrowed it from Thomas Werner papers, and here references, and again, as you see, it's rather, all this stuff is rather recent. Well, when you get to my website and you'll check these slides, I now start to put this type of remarks, saying that this is a good subject for projects. So, well, I understand that it was kind of fast, going through those slides, but if somebody will pick it up, somebody, well, beyond this week when we'll be discussing projects and we'll get kind of seminar style presentations, if one of you will pick it up, it certainly would be good. So it's just one suggestion for possible project discussions. Okay, so now, so that was kind of reminder, yeah, it took half an hour, but reminder of what we'll be discussing, or what I missed first lecture. So now I'm getting to the third and fourth lectures, so it will be third, and I probably will do it for another, well, maybe 45 minutes, so it will be a little bit more than an hour. That will make a break for 15 minutes, and then will be another hour. And, right, so what I already mentioned, those reparameterizations and gauges. Now we'll kind of move slower and we'll see how they enter, but I'm now back to my problem, original problem, main problem of partition function computation. Well, main message which I can kind of advertise in advance and here is that belief propagation, which I introduced so far only as approximation, can actually be improved, and we can go from belief propagation to exact expression with belief propagation. We can correct for errors which we got in this approximation in a very systematic way. And in fact, full expression for partition function will be what we call loop series. So series of terms, so sum of finite number of terms, and first term in the series is more or less what we're getting from belief propagation. So it's a new understanding of why belief propagation is useful. So it will be, yeah, so all evaluations, all results which I'll be reporting in here or discussing, they're exact. So I basically will not be doing approximation, but I'll use, I'll get in a way to belief propagation in actually yet another way. Right, so we already learned that, and I mean, kind of bad news is that this belief propagation is clearly exact on a tree, but in a loopy case, well, that's what people thought. It's heuristic, and it is not exact for sure. But it works very well, and what I'll be presenting gives some arguments of why it works so well. And again, arguments through relations between exact and approximate for partition function. Or you can use this as a discussion of how we correct for BP systematically. I mean, for error which we are getting from BP. And well, it's actually based on my work, and that's how I got into this field more or less, with Volodya Cherniak. And let me walk you through that, and I'll try to make it slow. So my base model will be this type of model. On the other hand, practically everything I'll be describing here, of course, generalizable to all those other representations. These factor graph representations or Ising model representations. But I'll be working with this for some while with this model where again my variables are on edges, my original variables which are sigma p, and I'll be mainly assuming binary, but some generalizations, many statements are generalizable. So what I'll be doing a strange thing. Well, something which, well, probably will take some time to appreciate. Strange, but rather simple. Instead of focusing on this pattern, so I have graph, and I'll not be touching graph. I have factors, and factors are associated with vertices. But what I'll start doing, I'll start modifying factors, right? And I want in this modification, so I'll be changing them. And that's actually how I'll be changing. So it's a linear transformations. And transformation which involves those G's, which are called gauges, or reparameterizations. And of course, factors will be changed. So I go from that to this. It's not equality. But what I want to find transformations such that my partition functions stay invariant. So I change gauges, I change those reparameterizations, change those factors, but partition function stays the same, stay invariant. And well, I put it pictorially in the following way. So I basically, so what this transformation, what this linear transformation means? You can think of it as introducing many matrices, each actually two matrices associated with every edge. So at every edge I put a matrix, and it will be JB and GPAs, they are not the same. And those so there are two matrices at each edge, right? And I color them differently just to emphasize how many of those matrices. And what is the size of those matrices? If my alphabet is binary, so it's 2 by 2 matrices. And statement which is very easy to check is that if I pick those two matrices associated with each edge, basically as well, satisfying this relation, this is Kronecker symbol, right? Well, if those matrices are not singular, and that's what I mainly the case which I'll be considering, so invertible. Then GAP and GBA, just one is inverse of another. Okay? So statement is that if I modify my factor in this form, introducing any G's, however satisfying these notations, my partition function will stay invariant. Okay, so I'll not be changing partition function. And so we call it gauge invariance by analogy with what gauge invariance in theoretical physics is. Well, usually gauge invariance means that something is invariant. So you introduce degree of freedom, and it's a continuous degree of freedom. It's actually a huge degree of freedom. Well, you can think of it as like that. So of those two matrices at each edge, I basically pick one, absolutely arbitrary, not singular, and another one is just inverse, right? I still have a lot of freedom. And it's continuous freedom. But my partition function is invariant. And that's by itself is already, well, probably you can feel that it's useful. Why? Because maybe playing with those transformations, I can simplify my factor graph. I'm not changing graph, but my factors, I change my factors. And that's roughly an idea. Of course, if your factors are in general position, it probably will not, you'll not get to, I don't know, very super simple factors, but still, intuitively, you'll really see that there is some opportunity in that. And in fact, this transformation, we're not the first to figure it out. Well, in this formulation, I guess, we were first, but similar, very related type of ideas were, came under this name of A-parameterization. That's for specific model, and that's by Wainwright, Yakel, and Wilsky. And then Leslie Valland, well, he's rather famous. I think he was Turing Award a couple of years ago, computer scientist from Harvard. He introduced something which is called holographic transformation, also for very special type of models, actually for planar graph models. And by the way, I'll get to some of that in the last two lectures. So they have similar ideas. So now, but let's see where it brings us. And actually, let me try to introduce it, to play a little bit with those factors in a different way. Not in a way I introduce this invariance in here, that's our way, but following Martin Wainwright. Martin is, by the way, at Berkeley, he's professor of computer science. And, right, so I'll be doing it in steps, and it's, well, I call it 11, right, because it's not exactly what, well, it's another model, but more or less in the spirit of what they've been doing. So basically, I'll kind of, it will be also algebraic manipulation. So I'll be multiplying and dividing, and, here I multiply by the same thing, right? So I introduce some factors. Well, not incidentally, I put the same notation because those will be the same notation as in my case, because those are the same factors. Right, multiply, divide. There will be some number of transformations like that. Basically multiply, divide, and then I rearrange it a little bit, well, which is still innocent, right? Product of a ratio of products. And then I start doing, relating it to belief. So it's the first time when belief in this language appears. And, I put this BABG to emphasize that it's general. So it will not be belief propagation beliefs here. You remember, right? I introduced beliefs in my previous lecture. Generic beliefs, right? So here it's kind of in the same spirit. So I introduce beliefs in the following way. So I introduce this JB and JB8, and I'll be assuming that those matrices are not singular, and more or less I'll be assuming, the same relation that JB and JBA, just one is inverse of another. And I'll also introduce this, what later, think of it as just a notation for now. Basically, I introduce it for this object which I have in a denominator in here. Well, in fact, I probably should do it a little bit more carefully. So that's what I got from my partition function. It's all exact transformation. And now I multiply and divide by this newly introduced object, which I defined it here. So again, multiply and divide, right? So Z is a product over A, and it's product of A. So then this whole bits do not depend on sigma. So it's just a constant. So I can do that. Then I introduce something which, objects which will become beliefs associated with edges. Those are objects which will become, well, very soon will become beliefs associated with vertices. So that's my notation. And by the way, you can check immediately that if I sum this object over sigma b, I will get 1. So it's a normalization because of this, well, orthogonality of those gauges JB and GPA. And similarly here, because of this normalization, if I sum over all possible states sigma A, which is a vector, then for this object I'm also getting unity. So those beliefs, or probabilities. And then, no. Right, so I have this format, and what I have in here is a product of probabilities BA associated with vertex A, and right, and okay, so maybe I should make it a little bit more clear. So it will be another multiplication and division, which brings me from this slide to the next slide. But end result, and the PJ sigma is defined here. So it's a product of beliefs over edges. But the point is that so this whole expression, which I'm getting in here, can be interpreted. So this is a valid probability distribution by construction, because each of those are normalized, and I can think of them, well, because it's product, I can think of them as independent. So therefore, I can interpret all of that as an expectation over this probability distribution. Not myself, but Android. Yeah, so that's what I wrote in here. And this is a formula which, well, they got one right, Wilsky, and yeah, so they got this type of formula in their model, and it was those B's were called reparameterizations. But those beliefs associated with edges and vertices, they certainly can be thought of as probabilities, but there is no consistency between them for arbitrary G. Consistency, that's something like what I was writing in here, right? So relation between edge and vertex probabilities, beliefs. Okay, so now, now I can basically, well, it was to a degree, you might think of it as a side remark. It will be used a few other times in this type of expression. But well, basically, main message is that you can start playing with this invariance, keeping partition function invariant, and try to reinterpret this sum in various ways, and in particular, you can reinterpret it as an expectation of some ugly beast, or ugly, strange expression. But now let's see where we can go. So I'm now kind of back to my formulation. And my formulation is, again, maybe I'll jump backwards. Oops. So what I did, I modify F. So I did a linear transformation of F, introduced those gauges, reparameterizations, well, you may call them this way. And I basically require that those JB and GPA, one is inverse of another. And then I can directly check the partition function of my original model with F and partition function of this modified model. So now instead of this factor, I use whole thing, well, all of that as a factor, and that's what I wrote explicitly. I can check that partition function is exactly the same for those two models. And now this is a starting point for further analysis. Okay, so what do I get from here? Yeah, so that's, I just rewrote this expression, right? So by construction, the G's are selected in such a way that this is equal to that, and now I keep working with this expression. And so here, you should maybe pay attention to the following. So I have this, my original variable, sigma, and I also introduce the sigma prime variables. And okay, maybe I should back it up a little bit, again to this transformation. When I introduce those prime variables, I sum over them, and I do it for every vertex, and therefore, well, sigma AB is a variable, my original variable, which resides at H, and it's the same for, well, it just resides for H, and H is not directed. But when I did this transformation, I introduced summation, I was doing it for a particular vertex, so I was on one side of H. And if I'll be doing it on another side of H, doing the same transformation, I'll get another prime variable. So sigma prime AB and sigma prime BA are not the same in this notation.
What's the difference between them?
Well, it just, well, it's, if you wish, empty variable, so I sum over them. Right? So when I sum, it means that I'm not requiring, will be summation over sigma prime AB and sigma prime BA independent. Right? So I don't have any constraint. I go this way, so I introduce this transformation. I start from that and I substitute, well, this is modification of my factor. But again, I emphasize that this original variable sigma AB and new variable sigma prime, they're principally different. Sigma AB and sigma BA is the same. Sigma prime AB is not the same as sigma prime BA, just by construction, because of how I introduce this modification. And okay. And now I start exploring that. So what I do, I have a sum over my original variables in this expression. And now my original sigmas, there are all those possible, for binary case, I have n edges, 2 in the power n terms in this sum. I pick one of them. And actually which one I pick is that it's kind of arbitrary, but in particular I pick one. Well, this notation means that all sigma is a vector, and all components of this vector is plus or minus 1. I pick one term in this sum which corresponds to all components of this vector to be plus. And then there are all possible other terms. Well, I call it ground state, and I call those excited states, just a name. And I introduce a Z node, and Z node is basically expression which I have under the sum of this particular value of sigma. And I'm yet to play with the remaining degree of freedom G. So I already use some degree of freedom in G, right? So I require that JB and GB are inverse of each other. But still a lot of freedom remains. And I use this freedom in the following way. I use this freedom to force, to force certain condition which I put in here, and let me explain this condition and then, explain formally and then clarify why do I put this condition. So this condition allows me to fix this remaining degree of freedom. Maybe jumping a little bit ahead, this way of fixing those gauges will make those gauges completely equivalent to some, to BP, to belief propagation. But let me tell you what I'm doing here. So it's what is written here. So it's basically forcing certain contributions of that type under products. So I have products of different vertices. I pick one particular vertex, A. node A, and then there are there is summation over prime variables, but the sigma AB in all this sum may be arbitrary, right? So they cannot be all +1, but because I already put this term in here, but there may be any other things. And I try to kill or force to zero certain terms. Okay, what kind of terms do I force to zero? I do it in the following way. I pick one particular edge, and actually I'm doing it for, well, I pick vertex, node, and I pick one particular edge, AB, and I call it color. Well, color in this case is blue. Well, red is not color. Well, my ground state is not colored. So I pick one particular edge, and I put it to minus color. And then all other edges emanating from this vertex, I basically I force them to be +1. So this is one particular contribution in this sum, and I want it to be equal to 0. And I'm doing it for all vertices and all edges. And it's very straightforward to check that I have exactly enough degrees of freedom to satisfy those constraints. And now, what needs to be understood is why I'm doing that. And I'm doing it, there are two sides actually in this formula. So one is to say that this particular way of fixing gauges will bring me back to the belief propagation equations which I was discussing before. But another is to explain the meaning of that. So let me start from a second. And let's see.
So as they all exist in those members, so just because we take current state with sigma all +1, that means that for each of other components there would be one of sigma is -1, right?
Yeah, so there are all components with all possible sigmas. Of course, yeah, they're all there are all possible contributions, and for general F they are non-zero. So it's like all possible. I
So that means that for each member in the fluid sum there is a component of state which is equal to -1. True.
Because I selected this +1, which means that one component should be -1, at least one. But here I'm doing it, I consider it locally. I pick just one vertex and I look at the surrounding of this vertex. And, because I have a product in here, so that's my reason for doing it. And I basically shouldn't worry about all classes. But I worry. I basically try to force to zero all terms where at least one edge is minus, is colored. But let me try to explain it kind of graphically. I'll be writing it in here, and I actually will be using color because it's exactly what I'm doing coloring. So let me consider, for example, this graph, and let me start coloring, and coloring, blue will be coloring. So basically, what I'm saying that with those conditions, my partition function is a sum of all possible coloring. And there is one term which I pull aside, which is not colored, right? And then will be, for example, this term. When I have +1s at all edges, but this one edge. And if I'm telling you that I can force this term, all those terms, all local terms of this format to be equal to 0, it means that this contribution will certainly be 0. Why? Because if I go from this vertex and I basically check this formula, I immediately get that never mind what for each of these contributions, expression under this sum will be a product of terms and product of local terms, right? And when this term, one of them, is equal to 0, the whole product is 0, right? So this particular configuration will be 0. Again, if I enforce this condition for all vertices and all edges, coloring only one edge, one edge linked to this vertex. But what if I consider this contribution? So I color two edges. Well, here I'll certainly, for this term, I'll not get 0. Well, it's not one of those, so I didn't put it to 0. I didn't pose it to be 0. But remember, this is each contribution to this partition function, to the sum, is a product of terms. And here, I again have trouble, not trouble, I have 0, exactly 0 because of this contribution from this vertex. And therefore, the only way I'll get non-zero contribution is when I get a loop. So in other words, all vertices which are part of a colored subgraph mark a contribution to this sum. If the subgraphs form a loop, and loop may be like that, then I'll not get 0. Well, if I'll keep going and, for example, introduce this type of coloring, it will be 0 again because I have what I'm calling loose end. But if I'll close it, for example, like that, so coloring would be like this, then I'm good okay. And you may ask why I'm doing it. Now imagine that I have a tree. If I have a tree, whatever tree I have, I certainly don't have any loops, right? Therefore, all those conditions, if I manage to satisfy all of them, will lead to 0 for any coloring on the tree, right? Because on the tree, I basically cannot get rid of loose ends. What I call loose end is again something like that. So this is also 0 contribution. But on the tree, I don't have this way, and therefore, in the case of a tree,
just two.
Well, there will be only one configuration, which is non-zero, only that one. All colored will be 0 because of this condition. Yeah, so that's actually reason for us, to introduce this type of gadgets. And the remarkable thing is that you can achieve it by, you can basically satisfy those constraints. Now there is some algebra involved in checking that what I'm getting here is exactly belief propagation. Well, according to this explanation, I'm basically, if those expressions indeed do this remarkable job prohibiting me from having any of this colored contribution unless they are loop, then it basically automatically means that on the tree I have nothing but this first contribution, and of course I start feeling that those gauges should have the same expression as those belief propagation equations which I showed you in the previous lectures, and indeed there is a very formal algebraic way to verify. Well, I don't know if you remember, but through some substitution and transformations, which I probably don't want to emphasize, too much, because it's just algebra, and it really, if you want to check it, you need to go through that yourself. But you're getting, well, you may remember this type of equation. Actually, I probably, let me show you so I'm getting this. So my statement is that all those conditions.
Sorry, you just introduced new condition for metric J.
Right. And I'm saying that exactly that. So let me restate it again. So my matrix J. So I conditioned J in 2 steps. So first of all, I introduce this transformation and I require that JB and GBA as matrices, the inverse of each other. Right?
This is the first problem.
That's the first condition. That's to keep partition. Basically, any transformation of this type keep partition function invariant. And then I'm going into this second stage of gauge fixing, and I'm doing this type of, well, I'm doing it for all vertices and for all edges, directed edges emanating from this vertex. Those are initial conditions, and my statement is that I have enough freedom to satisfy all of them. And when I massage it a little bit further, well, in particular for binary alphabet, choosing this type of reparametrization for elements of matrix through this ethos, I'm getting equations which are basically absolutely equivalent to equations which, let me jump back to, which we got in a second lecture. Yeah, those are equations which we got in the second lecture when we discussed a tree, right? So here I derive them from a tree. Today I didn't derive them from a tree. I derived them from this, well, coloring rules.
As I understood, this coloring rules generate a tree from.
Well, reason, well, not exactly, but close.
It is sort of simultaneous
Say again?
it is sort of simultaneous statistical symbol.
I don't know. I mean, what do you mean by that? So once again, so trees. Well, if I would have, if my graph is a tree, then those. Well, if my graph is a tree, then enforcing those conditions kill all those terms, force them to be zero, all of them. And in the case of a tree, my whole partition function is reduced just to one term. But in a general case, I have those loops remain. And actually, well, I'll get into more details of what do we get. We call them, like, all those possible subgraphs, generalized loops. So basically, all subgraphs of original graph such that each vertex have degree at least 2.
So basically, when loops are large, that means that all other components will be smaller than ground state, and like.
Okay, well, you're jumping ahead a little bit, right? So you already started thinking about how to use it. But yeah, so for now, it's just exact statements and exact transformations. And again, emphasize important thing to appreciate is that it is exact transformations, and if our graph is a tree, then we are done. We have only one term, and the computations are easy. And indeed, we are getting these belief propagation expressions. By the way, beliefs. Well, in this language, it's the first time when I introduce beliefs, and beliefs are more or less naturally coming expressed through gauges. Well, again, it's those are written in here, and one important link is that when I was using this reparametrization, I'll get back to that. I also got those beliefs in some very different ways. So now, how do we? Right. So let me. So that was one way, and one way of getting this gauges fixed in an interesting way, in belief propagation way. So it was one way to explain on a loopy case what is special about belief propagation. But let me introduce the second way, a second kind of logical way which will get us to the same result, but it's a little bit different logic. Again, I'm back to my expression where I'm back to a situation when I didn't fix gauges yet. Okay, so it's, well, I fix gauges in the sense that at every edge those two matrices one is inverse of each other, but otherwise I didn't use this formula from the previous two slides. And again, I select what I call ground state, non-colored, red, non-colored, and all others colored are blue. And then let me do the following. Let me completely forget about this term, I mean all those terms, focus on this red one, it's only one term. And it depends, of course, all of them by construction do not depend on gauges, right? That's by construction. I basically put those gauges to keep this partition function invariant. But now, let me pick only one term, and this one term does depend on gauges. And let me try to minimize this dependence. If I'll find particular value of this g for which the z naught is least dependent of g, then it probably will be not bad, right? Well, intuitively, I want to minimize the z naught, minimize, maximize, well, extremize. So find extremum of the z naught with respect to g. And of course, well, I have those constraints on g that there are two gauges on each edge, and again, the one is inverse of another, I mean matrices. So I want to do it under those constraints. I didn't put algebra in here, but that's roughly what I'm doing. Well, I introduce this, yeah, well, I'm doing exactly what I said, but it's a little bit, well, to make it accurately, again, satisfy those conditions, and then if I want to do optimization, I need to do it with respect to epsilon. But in any case, if I do that, so I pick this one term and look for stationary point of this term with respect to gauges within this family of gauges which are at each edge, JB and GBA are inverse of each other, I'm getting a set of conditions which are exactly equivalent to belief propagation equations. And it's again, it's very intuitive, and it actually brings us back to this variational derivation of belief propagation. So belief, well, by construction, I cannot expect this one term to be independent on G. Only all of them, and in some, do not depend on G. But because I kind of want to approximate this whole sum by this one term, a good idea is to find this extremal G for which there is least dependence on G. And what is least dependence is extremal point, right? So I basically, well, I'm looking for stationary point. And this beta free energy, as you remember, is not convex, so potentially it may have many stationary points. Actually, we have minimum, maxima, we have saddle points. In principle, if I pick any of those, well, I may have multiple solutions for this stationary point condition, and those multiple solutions will correspond to those stationary point of beta free energy, not necessarily mean. So that's a second interpretation, and again, it's a direct algebraic check which you need to do to verify that this what I just told you is correct. Okay, so I'm not putting on the slides because it's kind of a bit ugly algebra, but that's certainly correct. And there is a third way through reparametrization, and probably it was pedagogical mistake to put reparametrization because those first two cases, but in any case that's what I did. Remember this green stuff, right? So I was doing this exercise of transformations, right? So that were reparametrization from one right and others. But I kind of stopped short. So I was doing these transformations and I didn't introduce consistency. So I was emphasizing that this G is arbitrary. And now I am jumping over to the third way, basically to the same formula which I had before. And now, in addition, yeah, so that's more or less, I wrote what I had before, so it was exact transformation. Well, that's for product of functions, and that for partition function. So it should hold for any b's, bg. But now, if additionally I introduce this consistency between vertex belief and edge belief, then condition for those beliefs will be equivalent to beta free energy. And actually the whole series which I'll get, because I'll get not one term but many terms, will be equivalent to series which will be, which I'm getting to what I call loop series, which will consist of this type of color contributions. Okay, but in any case, so it's there are at least 3 ways to arrive at this loop series, and probably there are more. But what is this loop series? Well, back to my coloring interpretation, and actually getting, well, it's more or less the same graph. And here, I don't know if you can see it, instead of coloring, I just put bold. So those are generalized loops which are remaining contributions. So many contributions, I kill them. So for example, contribution which would be like that, contribution like that, contribution like this, even that, but not this. This one, of course, enters. So many contributions we kill the 0 by construction, but those are remaining. And remarkably, because I computed those gauges, well, I assume that I solved those equations, those belief propagation equations. I know those gauges, and I found them. All those contributions, except I can compute them explicitly. And you may say, okay, maybe that's it. Maybe he solves this problem of computing partition functions. Of course not, because there are exponentially many of those contributions, right? Still remaining. But it's already serious reduction, right? And again, each term is associated with a loop, which we call generalized loops. Once again, kind of informal definition. This is a subgraph such that, subgraph consisting of vertices and edges, such that each vertex, each colored vertex, have at least 2 colored edges associated with it, emanating from it. At least 2, well, this one has 3, right, in this structure, in this type of color. So that's definition of those generalized loops. So this particular format is actually very simple. In the case of binary alphabet, it's very simple expression and actually rather intuitive for each term in this loop series. So those C's are generalized loops. So RC have a very simple explicit format, and it may be basically expressed through marginal, through expectations which you compute with this belief propagation, with belief propagation beliefs, those B's, yeah, so that's a nice formula. And we'll be discussing later on how to use this formula, but for now, that's the main message. So we have this loop series, and loop series is based on BP. BP selects the first term in this loop series. So if I forget about all those other contributions, take only one, that will be my estimation for belief propagation, which I got from belief propagation. In particular, estimation which Didier Freeman-Weiss got for what they call optimal beta free energy. But there are all those corrections, and corrections are non-zero in general, and well, that's very nice because potentially it gives me opportunity to estimate how good or bad belief propagation is. Yeah, so there are number of comments, and here all terms calculated within BP, so explicitly. BP is exact on the tree. On the tree, all those contributions are 0, as we discussed. Yeah, so you interpret BP as a gauge fixing, so it's one of those interpretations. Well, if you choose other gauges, you will not fix those equations. You can also do it, but then you'll get more contributions. And actually, there are interesting stories yet unexplored. If it is better or not in terms of approximation, but here in any case, I fix them, all those gauges to be BP. Yeah, so another remark, and I don't know, this remark is for those who know what high temperature expansion is. So there is a certain expansion in physics, which is, well, for very special type of model, for Ising model without magnetic field, which is called high temperature expansion. It's actually expansion around, well, this so-called paramagnetic solution. An expectation all spins, so spin variables are equal to 0. Well, this loop series is equivalent to this high temperature expansion for that case, but in this case, belief propagation solution is basically a trivial solution, very simple solution. So you may think of it as a generalizing this high temperature expansion. Okay, so I probably should call, yeah, this natural time for break, because I'm basically done with this third lecture. Okay, so let's do break for 15 minutes.